Settle into your favourite spot, close your eyes if you haven't already, and let your breathing find its natural rhythm. Tonight, we're embarking on a journey through one of the universe's most profound mysteries, a question that has puzzled physicists and philosophers for over a century. Before we begin, I'd love to hear from you in the comments. What do you imagine the earliest moments of the universe felt like? Was there silence? Was there light? Was there a gentle stirring like the first movement of a sleeping giant? Share your thoughts. I always enjoy reading them in the morning, and your perspectives often inspire future episodes. Our question tonight is deceptively simple yet beautifully complex. Can time exist without space? It's the kind of question that makes the mind wander through cosmic corridors, past the familiar boundaries of our everyday experience. Picture yourself floating gently in the vast darkness between stars, where space seems infinite and time moves at its own mysterious pace. What we'll discover together is that this question touches the very heart of reality itself, leading us into realms where our most basic assumptions about existence begin to dissolve like morning mist. The beauty of this question lies not just in its profundity, but in how it connects to your immediate experience right now. As you listen to these words, time seems to flow steadily forward, carrying you from one moment to the next. You exist here, in this particular location in space, at this specific point in time. Yet as we'll explore tonight, this apparently simple fact may be one of the most mysterious phenomena in the entire universe. Imagine, if you will, standing in an empty field on a clear autumn night. The air is crisp but not cold, carrying the faint scent of distant wood smoke and the subtle perfume of dried grasses. A gentle breeze moves across the field, barely strong enough to rustle the tall stems around you. Above you stretches an endless canopy of stars, each one a distant sun, burning quietly in the cosmic dark. The Milky Way arcs overhead like a river of light, so clear and bright that you can see its spiral arms stretching from horizon to horizon. The silence here is profound, the kind of deep quiet that seems to have weight, settling gently around you like a soft blanket. It's not the dead silence of an empty room, but the living stillness of a universe at peace. Occasionally you hear the distant call of a night bird, or the soft whisper of wind through nearby trees. These sounds don't break the silence so much as accent it, like brush strokes on a vast canvas of quiet. As you gaze upward, time feels different here. Each second stretches luxuriously, unmarked by the usual rush of daily life. The stars appear fixed, eternal, as if they've held their position since the beginning of everything. Yet somewhere in the back of your mind you know they're moving and spinning on their axes, orbiting around galactic centers, racing through space at incredible speeds that would make your head spin if you truly comprehended them. The light reaching your eyes left some of these stars when dinosaurs walked the earth, when your ancestors were learning to make fire, when the pyramids were young. Time and space seem inseparable in this moment, woven together like threads in an invisible tapestry. The distance to the stars gives meaning to time, the years their light has travelled to reach you. The passage of time gives meaning to space, the evolution of the universe that created the very atoms in your body from stellar furnaces billions of years ago. But what if we could unravel those threads? What if we could separate time from space, like carefully pulling apart the layers of an ancient manuscript written in a language we're only beginning to understand? This is the thought experiment that has captivated some of the greatest minds in physics, a puzzle that grows more intriguing the deeper we venture into its mysteries. To understand whether time can exist without space, we must first understand how these two concepts became so intertwined in our scientific thinking. For most of human history, spanning countless generations of curious minds, time and space seemed like completely separate things. Time was the steady rhythm of days and seasons, the aging of faces in family portraits, the growth of trees from saplings to giants. Space was the distance between villages, the height of mountains touching the sky, the vastness of oceans that seemed to stretch beyond the edge of the world. This intuitive separation made perfect sense to our ancestors, and it guided scientific thinking for centuries. When ancient astronomers looked up at the night sky, they saw time as the movement of celestial bodies across the dome of space. The sun rose and set, marking the passage of days. The moon waxed and waned, tracking the months. The constellations wheeled overhead in their eternal dance, marking the passage of years and seasons. Isaac Newton, writing his mathematical laws in the late 1600s while sitting in his garden in England, imagined time as a cosmic metronome, ticking steadily throughout the universe at exactly the same rate everywhere. Whether you were on Earth watching an apple fall from a tree, or on the moon bouncing in the low gravity, or racing through the cosmos on a comet's tail, Newton's time flowed onward like a great river, indifferent to everything around it. This time was absolute, universal, flowing at the same rate for every observer in the universe, like the steady beat of some cosmic drummer that never missed a step and never changed tempo. Similarly, Newton envisioned space as a vast, empty stage, a three-dimensional theatre where the drama of physics played out. Objects moved through this space, forces acted across it, planets orbited in their elliptical paths, but space itself remained unchanging, eternal, absolute. It was like an infinite coordinate system, marked with invisible grid lines that never shifted or warped. You could measure distances in this space with perfect certainty, knowing that a meter here was exactly the same as a meter there, now and forever. Time flowed, space endured, and never the two shall meet. They were like parallel rivers, flowing side by side but never mingling their waters. This elegant picture worked beautifully for describing everything from falling apples to orbiting planets. It painted the universe as a grand clockwork, predictable and orderly. Wind up the cosmic clock, set the planets in motion, and the future was completely determined by the precise application of mathematical laws. The mathematics was clean, the concepts were intuitive, and for over 2 centuries, this framework guided humanity's understanding of the physical world with remarkable success. Newton's laws could predict the return of comets decades in advance, calculate the tides, explain the motion of pendulums and spinning tops. They revealed that the same force that made apples fall also kept the moon in orbit around the Earth. This was the first great unification in physics, the realization that earthly and celestial phenomena obeyed the same fundamental laws. It was a breathtaking insight that hinted at the deep unity underlying the apparent diversity of natural phenomena. But deep in the heart of this clockwork universe, a subtle mystery was waiting, like a tiny crack in a perfect crystal that would eventually split it apart entirely. Light, that most fundamental phenomenon, behaved in ways that didn't quite fit Newton's picture. When scientists tried to measure how fast light travelled, they discovered something puzzling that would eventually revolutionize our understanding of reality itself. Throughout the 1800s, as scientists developed increasingly sophisticated ways to measure the speed of light, they kept running into the same puzzling result. The speed of light seemed to be the same no matter how fast you were moving when you measured it. This was deeply strange, like discovering that no matter how fast you ran toward or away from a train, its whistle always sounded exactly the same pitch. In Newton's universe, this should have been impossible. If you were moving toward a source of light, you should measure the light as moving faster than if you were standing still. If you were moving away from the light source, you should measure it as moving slower. This is exactly what happens with sound wave. The pitch of an ambulance siren changes as it approaches and recedes because of the Doppler effect. But light seemed to ignore this common sense expectation entirely. Various physicists investigated the possibility that light propagated through a medium they dubbed the luminiferous ether, an invisible substance that filled all of space and carried light waves the way air carries sound waves. This ether would have been the absolute reference frame that Newton's physics seemed to require, the cosmic coordinate system against which all motion could be measured. But nobody could find evidence for any such ether, despite increasingly clever experiments. Scientists built incredibly sensitive devices to detect Earth's motion through this supposed ether as our planet orbited the Sun. They reasoned that at different times of year, Earth should be moving through the ether at different speeds, creating measurable effects on the speed of light. But experiment after experiment found nothing. The ether remained stubbornly undetectable. The most famous of these experiments was conducted by Albert Michelson and Edward Morley in 1887. They built an ingenious device called an interferometer that could detect incredibly tiny changes in the speed of light, changes so small they would be like noticing that a cross-country runner had taken one extra step in a marathon. But their results were shocking. There was no change at all. Light travelled at exactly the same speed in every direction, regardless of Earth's motion through space. So they were forced to invent increasingly complicated reasons why this ether should be undetectable. Maybe the ether was partially dragged along by moving objects. Maybe measuring devices contracted in the direction of motion through the ether in just the right way to hide the effect. Maybe time itself ran at different rates for observers moving through the ether. These explanations became increasingly contrived, like adding epicycles to epicycles to save a failing theory. In the early 1800s, a young patent clerk named Albert Einstein was pondering this strange behaviour of light, day after day as he sat in his office in Bern, Switzerland, examining patent applications for electromagnetic devices and synchronization systems. His mind wandered to deeper questions. What would it be like to travel alongside a beam of light? If you could somehow catch up to a light wave and ride along with it, what would you see? Would the electromagnetic field appear frozen, like a snapshot of waves on a still pond? These daydreams led Einstein to a startling realization that would change our understanding of reality forever. Einstein's contribution in 1905 was to point out that the ether had become completely unnecessary and that we could better understand the laws of physics without it. All we had to do was accept a completely new conception of space and time. The key insight was that there is an absolute speed limit in the universe, speed at which light just happens to travel when moving through empty space. This speed, approximately 300 million meters per second, isn't just the speed of light, it's the speed of causality itself, the maximum rate at which the information can travel from one point to another. Nothing with mass can reach this speed, and nothing can exceed it. But more importantly, this speed limit revealed something profound about the nature of reality itself. Einstein realized that the constancy of light speed could only be explained if space and time were not the separate, absolute entities that Newton had imagined. Instead, they must be different aspects of something more fundamental, space-time. Einstein's breakthrough was to recognize that what we call space and what we call time are really different aspects of a single unified fabric. Space and time took on new meanings with the Lorentz transformation and special theory of relativity. Like shadows cast by a four-dimensional object onto different three-dimensional screens, space and time are projections of space-time that look different depending on your point of view, specifically depending on how fast you're moving. This revelation was beautifully captured by Hermann Minkowski, Einstein's former mathematics professor, who declared in 1908, "Henceforth, space for itself and time for itself shall completely reduce to a mere shadow, and only some sort of union of the two shall preserve independence." Picture space-time as a gently flowing river. From the riverbank, the water appears to move in one direction, forward in time, but if you were to somehow step outside of the river entirely and view it from above, from a perspective beyond the normal flow, you would see that past, present, and future all exist simultaneously, stretching out like a vast landscape. Each moment is a cross-section of this four-dimensional river, and what we experience as the flow of time is really our journey through this eternal structure. The unification of space and time had immediate and startling consequences that challenged everything we thought we knew about reality. If space and time were truly unified, then anything that affected one must also affect the other. Moving through space must affect the passage of time, and the presence of matter and energy must warp both space and time together. These weren't just abstract theoretical possibilities, they were concrete, measurable effects that could be tested in the laboratory and observed in the real world. Time dilation became one of the most famous predictions of relativity. Clocks moving at high speeds run slower than stationary clocks. This isn't just a malfunction of the clocks, or an illusion of perception. Time itself literally passes more slowly for objects in motion. The effect is subtle at everyday speeds. If you spent your entire life travelling in a jet airplane, you would age only a few millionths of a second less than someone who stayed on the ground. But as speeds approach the speed of light, the effect becomes dramatic. A traveller moving at 9% of light speed would experience time passing 7 times more slowly than someone at rest. What felt like 1 year to the traveller would correspond to 7 years for the stationary observer. Length contraction is the spatial counterpart to time dilation. Objects become shorter in the direction of their motion when viewed by a stationary observer. A meter stick flying past you at high speed would appear to be less than a meter long, squashed like an accordion in the direction of motion. Again, this isn't an optical illusion or a measurement error. Space itself is affected by motion. These effects reveal that there's no universal now that applies everywhere in the universe. Events that appear simultaneous to one observer may occur at different times for another observer moving at a different speed. The universe doesn't have a single universal clock ticking away the same time for everyone. Instead, each observer carries their own time, their own now, their own slice through the four-dimensional space-time loaf. Einstein's insights about space-time grew even more profound when he turned his attention to gravity. In his general theory of relativity, published in 1915 after years of intense mathematical struggle, he revealed that what we experience as the force of gravity is actually the curvature of space-time itself. Special relativity is the theory of a fixed, flat space-time without gravity. General relativity is the theory of dynamic space-time, in which curvature gives rise to gravity. This was perhaps the most radical reimagining of reality in the history of human thought. Gravity wasn't a force pulling objects together across empty space, as Newton had envisioned. Instead, massive objects actually warp the fabric of space-time around them, creating curves and valleys in the four-dimensional landscape of reality. Imagine space-time as a vast, soft fabric stretched taut, like a cosmic trampoline extending infinitely in all directions. When you place a heavy object, a star, a planet, a black hole, on this fabric, it creates a depression, a gentle valley in the otherwise flat surface. The heavier the object, the deeper the depression. Other objects following the straightest possible path through this curved space-time, what mathematicians call geodesics, naturally roll toward the depression. This rolling motion is what we experience as gravitational attraction. But here's where the story becomes even more fascinating. The curvature doesn't just affect space, it affects time as well. Time runs more slowly in regions of stronger gravitational fields. Clocks on the surface run more slowly than clocks in outer space. Clocks sitting on the surface of the Earth run slightly slower than an identical clock orbiting high above the atmosphere. This gravitational time dilation has been measured with atomic clocks accurate to billionths of a second, confirming Einstein's predictions with extraordinary precision. Time itself becomes malleable, stretched and compressed by the presence of matter and energy. Near massive objects, time dilates significantly. On the surface of a neutron star where gravity is billions of times stronger than on Earth, time would pass noticeably slower than it does here. What felt like an hour on the neutron star's surface would correspond to several hours as measured by a distant observer. This means that time is not the universal steady metronome that Newton imagined. Instead, time is dynamic, flexible, intimately connected to the geometry of space. The stronger the gravitational field, the more dramatically time dilates. Near the event horizon of a black hole, time slows to such an extreme degree that, from the perspective of a distant observer, it would appear to stop entirely. An astronaut falling toward a black hole would appear to freeze at the event horizon, their image growing dimmer and redder as time stretched toward infinity. Black holes represent perhaps the most extreme examples of space-time curvature, regions where Einstein's equations predict that space and time become so distorted that they almost seem to lose their meaning entirely. At the centre of a black hole lies what physicists call a singularity, a point where the curvature of space-time becomes infinite, where the normal laws of physics break down completely. But even more mysterious is what happens to time near a black hole. As you approach the event horizon, the point of no return, time dilation becomes more and more extreme. From the perspective of someone watching from a safe distance, a falling astronaut would appear to slow down dramatically as they approach the event horizon, their movements becoming more and more sluggish until they appeared to freeze completely at the boundary. Yet from the astronaut's perspective, nothing unusual happens. They pass through the event horizon in finite time, experiencing nothing special at that moment. Time continues to flow normally for them, even as they fall toward the central singularity. It's only the outside observer who sees time stretch toward infinity. This creates a profound puzzle about the nature of time itself. Whose perspective is correct? The outside observer who sees the astronaut frozen forever at the event horizon, or the falling astronaut who experiences crossing into the black hole in finite time? The answer, according to relativity, is that both perspectives are equally valid. There is no universal correct time, only the proper time experienced by each observer along their own world line through space-time. Black holes also raise deep questions about the relationship between space, time, and information. According to quantum mechanics, information cannot be destroyed. But what happens to the information carried by matter that falls into a black hole? If the black hole eventually evaporates through Hawking radiation, where does that information go? This black hole information paradox has puzzled physicists for decades and continues to drive research into the fundamental nature of space-time. As beautiful and successful as Einstein's space-time proved to be, it faced a profound challenge when scientists began to explore the quantum realm, the bizarre world of atoms and subatomic particles. In this microscopic domain, the classical notions of space and time begin to break down in fundamental ways that challenge our deepest assumptions about the nature of reality. Quantum mechanics describes a reality where particles can exist in multiple places simultaneously, existing in what physicists call superposition states. A quantum particle doesn't have a definite position until it's measured. Until that moment, it exists in a ghostly combination of all possible positions, like a probability cloud spread throughout space. The act of observation itself changes physical outcomes, collapsing the wave function and forcing the particle to choose a specific location. Even stranger, quantum mechanics reveals that particles can be entangled with each other in ways that seem to defy our understanding of space and time. When two particles are entangled, measuring one particle instantaneously affects the other, regardless of how far apart they are. Einstein famously called this spooky action at a distance, and it troubled him deeply because it seemed to violate the principle that nothing can travel faster than light. In quantum mechanics, time is universal and absolute. Its steady ticks dictate the evolving entanglements between particles. The Schrödinger equation, which governs quantum evolution, treats time as an external parameter, like the conductor of an orchestra keeping time while the quantum symphony plays out. But in general relativity, time is relative and dynamical, a dimension that's inextricably interwoven with directions x, y, and z into a four-dimensional space-time fabric. This creates what physicists call the problem of time, a fundamental incompatibility between our two most successful theories of physics. Quantum mechanics regards the flow of time as universal and absolute, whereas general relativity regards the flow of time as malleable and relative. It's like trying to merge two different languages that have fundamentally different grammatical structures. The challenge becomes even more acute when we try to understand what happens at the very smallest scales of reality, distances so tiny that quantum effects and gravitational effects become equally important. At these scales, approaching what's called the Planck length, about 10⁻⁵ meters, our current understanding of space-time itself may break down entirely. At the Planck scale, quantum fluctuations in the fabric of space-time become so violent that the very notion of a smooth, continuous space-time may lose its meaning. Space and time may become foamy, granular, made up of discrete chunks that fluctuate in and out of existence like bubbles in a cosmic soup. The familiar concepts of distance and duration may dissolve into something more fundamental and strange. The conflict between quantum mechanics and general relativity has driven physicists to search for a theory of quantum gravity, a mathematical framework that could unify these two pillars of modern physics. This quest has led to some of the most radical ideas in the history of science, concepts that challenge our most basic assumptions about the nature of reality. String theory, perhaps the most famous approach to quantum gravity, proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings. These strings exist in a higher dimensional space, with extra dimensions curled up so small that we can't perceive them directly. different vibration patterns of these strings correspond to different particles and forces, like different notes played on a cosmic violin. In string theory, space and time emerge from the collective behavior of these fundamental strings. The smooth spacetime of general relativity is like the surface of a calm ocean, apparently continuous and uniform, but actually made up of countless tiny discrete components. At the deepest level, space and time might not be fundamental at all, but rather emergent properties of something more basic. Loop quantum gravity takes a different approach, proposing that the fabric of space and time is made of a network of extremely small discrete chunks, or loops. In this view, space-time isn't the smooth, continuous fabric that Einstein envisioned, but rather a kind of cosmic mesh, woven from discrete bits of space and time that can't be subdivided further. One of the remarkable aspects of loop quantum gravity is that it appears to eliminate time entirely. In this framework, the fundamental equations of physics make no reference to time. Instead, they describe relationships between different physical quantities, how one thing depends on another, but not how things change over time. Time becomes an emergent property that arises when we consider the collective behavior of these fundamental loops. As physicists have wrestled with these challenges, some have begun to ask a radical question. What if time isn't fundamental at all? What if time, like temperature or pressure, is an emergent property that arises from something more basic? This might seem impossible to imagine. How can physics work without time? The answer lies in thinking about time as we think about other emergent phenomena in nature. Consider the temperature of a gas. Temperature seems like a fundamental property. Hot feels different from cold, after all. Your skin can sense the difference immediately, but at the microscopic level, temperature is just the average kinetic energy of countless molecular motions. There's no such thing as the temperature of a single molecule. Temperature emerges from the collective behavior of many particles, but it has no meaning at the individual particle level. Similarly, the pressure of a gas emerges from countless molecular collisions with the walls of a container. Each individual collision is a simple, instantaneous event described by Newton's laws of motion. But when you have trillions upon trillions of such collisions happening every second, the emergent property we call pressure appears. Pressure is real and measurable, but it's not fundamental. It's a statistical property of large collections of particles. Time might be like temperature and pressure, an emergent property that arises when we consider the collective behavior of more fundamental entities. Just as we can derive the laws of thermodynamics from the statistical mechanics of molecular motion, perhaps we can derive the flow of time from the dynamics of more basic, timeless components of reality. Some approaches to quantum gravity suggest that at the most fundamental level, the universe is described by timeless mathematical relationships. Jacobi's action principle, for instance, describes physics in terms of geodesics on a configuration space that correspond to physical motions of constant energy. This approach makes no reference whatsoever to external notions of time. Indeed, time pops out of your equations as a secondary concept. Even more remarkably, recent research suggests that all of classical physics, including Einsteinian relativity and gauge theories, can be formulated in this timeless manner. It's like discovering that you can write all the music ever composed without using the concept of rhythm. That rhythm emerges naturally from the relationships between the notes themselves. A particularly elegant approach to understanding time's emergent nature comes from groundbreaking work by physicists Don Page and William Wouters. In the 1980s, they discovered something remarkable that would fundamentally change how we think about time in quantum systems. They showed that an entangled system that is globally static can contain a subsystem that appears to evolve from the point of view of an observer within it. Their insight can be understood through a simple but profound analogy. Imagine a vast eternal photograph, completely static, never changing, existing outside of time. Now imagine that this photograph contains many clocks, each showing a different time. From the perspective of someone looking at the entire photograph from outside, nothing ever changes. The photograph simply exists, timelessly and eternally. But if you were somehow living inside the photograph, unable to see the whole picture, and you used one of the clocks to measure time, you would perceive change and evolution around you. As your internal clock ticked from 1 second to the next, you would see different parts of the eternal photograph, creating the illusion of temporal flow. The photograph itself never changes, but your journey through it creates the experience of time. This is precisely what Page and Wouters discovered could happen with quantum systems. Called a history state, such a system consists of a subsystem entangled with what you might call a quantum clock. The state of the subsystem differs depending on whether the clock is in a quantum state corresponding to different times, like having its hour hand pointing to 1, 2, 3 and so on. But the whole state of system plus clock doesn't change in time. There is no time, it's just the state. It does never change. In other words, time doesn't exist globally, but an effective notion of time emerges for the subsystem. The universe as a whole might be completely static and timeless, while still containing observers who experience the flow of time. In 2013, researchers at the Istituto Nazionale di Ricerca Meteorologica in Turin, Italy, successfully demonstrated this phenomenon experimentally. Ekaterina Mareva and her colleagues used photons to create a static quantum state that nonetheless contained the seeds of apparent temporal evolution. Their work showed that time is an emergent phenomenon for internal observers of a quantum system, but is absent for external observers. The implications of this research are profound. If the Page-Wouters mechanism is correct, then the flow of time that you experience right now, the sense of moving from past to future as you listen to these words, might be an illusion created by your entanglement with the rest of the universe. You are the clock. Your evolution through different quantum states creates the appearance of temporal flow. Recent research has revealed that quantum entanglement might play an even more fundamental role in the structure of space-time than previously imagined. There is a lot of evidence that entanglement plays a major role in the emergence of smooth space-time. Just as temperature emerges from molecular motion, space-time itself might emerge from patterns of quantum entanglement. This idea has found its most concrete expression in the IDS-CFT correspondence, a remarkable discovery in string theory. This correspondence shows that a theory of quantum gravity in a higher dimensional space can be exactly equivalent to a quantum field theory without gravity in a lower dimensional boundary. It's like discovering that a 3-dimensional hologram can be perfectly encoded in a 2-dimensional surface. In this holographic picture, space and time in the interior emerge from entanglement patterns in the boundary theory. The geometry of space-time, distances, curvatures, the very notion of interior space, is encoded in the quantum entanglement between particles living on the boundary. When particles on the boundary become entangled, space appears in the interior. When they become disentangled, space disappears. This suggests that spacetime is not fundamental but emergent, arising from more basic quantum information. The fabric of space and time might be woven from threads of entanglement, with each thread representing quantum correlations between distant parts of the universe. The smooth spacetime of our everyday experience emerges when these quantum correlations organize themselves in particular patterns, like how the smooth surface of a lake emerges from the coordinated motion of countless water molecules. On the timeless boundary of our spacetime bubble, the entanglements linking together qubits would presumably remain intact, since these quantum correlations do not require that signals be sent back and forth, but the state of the qubits must be static and timeless. This line of reasoning suggests that somehow, just as the qubits on the boundary of 8S space give rise to an interior with one extra spatial dimension, qubits on the timeless boundary of de Sitter space must give rise to a universe with time, dynamical time in particular. This brings us back to our central question: can time exist without space? The answer, as we've discovered, is subtly complex and beautifully paradoxical, like a Zen koan that reveals deeper truths the more carefully we examine it. In some sense, modern physics suggests that asking about time without space is like asking about the colour of a sound or the temperature of a mathematical equation. These questions seem meaningful on the surface, but they reveal conceptual confusions about the nature of the entities involved. What really exists is space-time, and slicing it up into space and time is merely a useful human convention, like dividing the electromagnetic spectrum into colours when it's really a continuous rainbow. At the level of everyday experience, space and time are so deeply intertwined that separating them may be conceptually meaningless. Every event in the universe can be described by 4 coordinates, 3 for space and 1 for time, but these coordinates are mixed up in ways that depend on the observer's motion. What one observer calls space and time will be different mixtures of space-time for another observer moving at a different velocity. Yet the quantum gravity approaches suggest something even more radical, that perhaps neither space nor time is fundamental. Loop quantum gravity is not alone in abolishing time. A number of other approaches also seem to remove time as a fundamental aspect of reality. In these theories, what we call spacetime emerges from more basic entities that are neither spatial nor temporal. Some theoretical frameworks describe reality in terms of pure information or quantum entanglement, abstract relationships that don't require space or time for their existence. Emergence theory, for instance, proposes that all of reality is made of information. Information is meaning conveyed by symbols. From this information theoretic perspective, space and time emerge together, like 2 sides of the same coin, from patterns in the flow of quantum information. In this view, the universe at its most fundamental level is like a vast quantum computer, processing information according to logical rules that exist outside of space and time. Space and time emerge when this information organizes itself in particular patterns, like how meaning emerges from the arrangement of letters on a page. The letters themselves aren't meaningful, it's their relationships and patterns that create meaning. Similarly, the fundamental bits of reality might not be spatial or temporal, they might be pure information or quantum relationships. But when these bits organize themselves in particular ways, they give rise to the emergent phenomena we call space and time. Some researchers have even suggested that consciousness itself might play a role in the emergence of time. This is perhaps the most speculative and controversial aspect of these new theories, but it deserves consideration as we explore the deepest questions about the nature of reality. The idea is that consciousness, with its ability to observe and process information, might be necessary for time to emerge from timeless quantum relationships. In some interpretations of quantum mechanics, observation plays a fundamental role in determining physical outcomes. The act of measurement collapses quantum wave functions, forcing particles to choose definite properties from among their quantum possibilities. If consciousness is necessary for quantum collapse, and if time emerges from quantum evolution, then perhaps consciousness and time are more intimately connected than we typically assume. This doesn't mean that consciousness creates time in some mystical sense, but rather that the capacity for observation and information processing might be a necessary component in the physical mechanisms that give rise to temporal experience. Some approaches to quantum gravity suggest that the universe is filled with micro-observers, quantum systems that constantly make measurements and collapse wave functions at the Planck scale. These might not be conscious in the way we understand consciousness, but they might play a similar role in the fundamental physics of spacetime emergence. This fundamental, primitive, yet highly sophisticated form of consciousness might steer the patterns in the quantum substrate toward more and more meaning and complexity. Eventually, this process expands into higher degrees of order such as nature and life as we know it. From there, life and consciousness keep expanding, growing exponentially into all corners of the universe. In this view, we are not separate from the process that creates time, we are participants in it. Every observation we make, every moment of conscious experience contributes to the ongoing emergence of time from the timeless quantum depths. We are both products of time and co-creators of time embedded in a cosmic process that is far stranger and more beautiful than our everyday intuition suggests. As our scientific understanding has advanced, the mystery of time has only deepened. Recent discoveries in physics have revealed layers of complexity that previous generations could never have imagined. The universe appears to be far stranger and more beautiful than anyone anticipated. In approaches like string theory's ADIS-CFT correspondence, physicists have discovered that a theory of gravity in one number of dimensions can be exactly equivalent to a theory without gravity in fewer dimensions. This suggests that the space-time we observe at low energies is an emergent phenomenon, like the apparently solid surface of a soap bubble that is actually made of thin films of liquid. These discoveries hint at a profound truth. The universe may be fundamentally holographic in nature. Just as a hologram encodes three-dimensional information in a two-dimensional surface, the three-dimensional space we inhabit might be encoded in information stored on a two-dimensional boundary at the edge of the observable universe. Even more remarkably, recent research suggests that black holes themselves might be holographic projections of information stored on their two-dimensional event horizons. The three-dimensional interior of a black hole, with all its spatial complexity and temporal evolution, might be completely determined by patterns of quantum information on the spherical surface surrounding it. This holographic principle has profound implications for our understanding of space and time. If space is emergent from information stored on boundaries, then the very notion of interior and exterior might be more flexible than we imagine. The space you occupy right now might be a projection of information stored elsewhere, perhaps And so we return to where we began, standing in that quiet field under the infinite canopy of stars. But now, after our journey through the deepest mysteries of physics, that simple scene carries profound new meaning. The starlight touching your eyes has travelled not just through space, but through space-time itself, a four-dimensional fabric that weaves together every moment and every location into a single, unified tapestry. The question we set out to explore, can time exist without space, has led us down paths that our ancestors could never have imagined. We've discovered that this seemingly simple question touches the very heart of reality, revealing that our most basic assumptions about existence may be beautiful illusions. Perhaps time cannot exist without space because both are emergent properties of something deeper, patterns in quantum information, relationships in a cosmic hologram, or the eternal dance of entangled particles that exist outside the flow of time entirely. Like the shadows cast by a fire on a cave wall, space and time might be projections of a higher dimensional reality that our minds can glimpse but never fully grasp. Or perhaps the question itself reflects the limitations of language and thought when confronted with the true nature of existence. In asking whether time can exist without space, we may be like someone asking whether the colour blue can exist without wavelength, seeking to separate things that are fundamentally unified aspects of a single phenomenon. What we've learned is that the universe is far stranger and more beautiful than our everyday experience suggests. The solid ground beneath your feet emerges from quantum fields fluctuating in ways that transcend space and time. The steady flow of moments that carries you from past to future might be an artifact of your own consciousness, a melody played by the quantum orchestra of your entanglement with the cosmos. As you drift towards sleep tonight, carried by the gentle rhythm of your breathing and the soft weight of gravity pulling you toward Earth's center, remember that you are participating in the most profound mystery in existence. Every heartbeat, every thought, every moment of awareness contributes to the ongoing emergence of time from the timeless depths of reality. You are not separate from this cosmic process, you are it. The universe is experiencing itself through your consciousness, creating time through your observation, weaving space through your movement. In asking whether time can exist without space, you are reality questioning its own nature, existence contemplating its own foundations, and in that questioning, in that wondering, something magnificent emerges, the recognition that the deepest mysteries are not problems to be solved, but symphonies to be experienced. The dance of space and time continues, eternal and ever-changing, carrying us all forward into the infinite unknown. Rest well, dear listener. Tomorrow's questions await, but for now, let yourself dissolve gently into the timeless embrace of sleep, where past and future converge in the eternal present of dreams. The universe will keep its secrets safe until you're ready to explore them again. Sweet dreams, fellow travelers in space-time. The journey continues.